Every year, thousands of amateur explorers spend millions on advanced scanning equipment, only to spend weeks sweeping their coils over sterile modern topsoil. They walk inches away from priceless buried history without ever realizing it. They fail because they assume today's topography matches the historical surface. They dig up modern aluminum cans and 20th century farm iron because the terrain of modern civilization is an artificial mask. Beneath that mask lie real, high-conductivity targets, hidden caches from British colonial expansions, lost Roman British coin hoards, and dissolved monastic treasuries. The fatal operational error most hunters make is the eyeball match. They take an 18th century hand-drawn map and crudely stretch it over modern satellite imagery until a couple of river bends or modern roads appear to line up. This introduces cartographic drift. A visual error of just 1.5 millimeters on a historic parchment scales up to a devastating physical miss of up to 500 feet on the ground. You can have the most powerful metal detector in the world, but if your search grid is structurally flawed, your sensors will find nothing. Extracting ancient history requires the practice of cartographic discrimination. To eliminate cartographic drift, we have to look at the mathematical root cause: geodetic datum incompatibility. Modern global positioning systems operate on a standardized framework called WGS 84. It uses satellite telemetry to model the Earth precisely as a curved oblate spheroid. Early mapmakers did not have modern algorithms. They used uncalibrated regional baselines, or ignored the curvature of the Earth entirely, treating the local horizon as a flat, two-dimensional plane. Because early maps assume a flat plane, moving outward from the center point of an old map towards its perimeter causes the spatial error to multiply exponentially. This is the vector expansion effect. Plotting an uncalibrated coordinate from a historic map directly into a modern GPS shifts the location by 200 meters. The map data must undergo a computational translation. To perform that translation, we first have to isolate the specific historical assets holding the spatial data, which differ greatly depending on where you are searching. This 19th century UK tithe map shows intricate micro-level property lines and structural layouts. Maps like this, along with first edition Ordnance Survey charts, are the gold standard for locating long-demolished structures, ancient boundaries, and the original sites of manors. This is a U.S. Civil War combat engineering sketch, drawn directly under combat conditions. Topographers mapped tactical details here, making these documents highly valuable for tracking temporary campsites, artillery breastworks, and specific retreat routes where caches were frequently dropped. While these documents contain highly specific burial markers, they are completely unreadable to modern sensors until they are mathematically anchored to the digital grid. Bridging that mathematical gap requires industrial-grade geographic information systems. Top-tier hunters use open-source software like QGIS, which allows for precise data manipulation and layer stacking. The first step in this environment is anchoring ground control points, or GCPs. These are persistent physical markers that exist on both the historic parchment and the modern satellite base layer. GCPs demand unyielding physical features. The rigid corners of a 400-year-old stone church tower or ancient stone bridge abutments provide permanent mathematical anchors. You have to actively avoid using trash filters, features like road intersections or river bends. Roads are constantly rerouted, and rivers naturally migrate across floodplains, which will skew the structural integrity of the entire map. Once the control points are set, we apply a transformation algorithm known as the thin plate spline, or TPS. TPS acts as a local elastic model. Instead of applying a uniform rigid warp to the whole image, it takes the hand-drawn map and stretches it precisely around your chosen control points, minimizing cartographic drift down to mere inches. Setting the output of that elastic transformation to a standardized metric grid, like WGS 84, generates clean coordinate data. The historical anomalies are now locked into a flawless digital search matrix. Even with perfect software calibration, one final barrier remains: anachronistic topography. The physical Earth itself mutates over the centuries. Take riparian migration. Decades of continuous bank erosion and sediment deposition shift river paths laterally. A target buried 50 feet from a river bend in 1750 could easily be hundreds of feet away from the modern waterline. In agricultural belts, there is plow zone dispersal. Intensive, deep plowing over 2 centuries catches shallowly buried coin hoards and drags them into long, linear scatter trails far from the original deposit site. In low-lying valleys, depositional aggradation occurs. Annual flooding deposits thick layers of alluvial silt, burying historical homestead floors beneath several feet of modern mud, rendering standard metal detectors completely blind. Geomorphic calculation acts as the ultimate real-world filter. You have to account for these environmental mutations before taking your search matrix into the field. The asphalt, the plowed fields, and the leveled commercial zones of modern civilization act as a temporary drape over the actual surface of the past. Extracting the targets beneath that drape requires the precise intersection of ancient parchment, digital computation, and environmental awareness. By stripping away the spatial errors of hand-drawn charts and anchoring them accurately over modern terrain models, you cut through the modern landscape mask to reveal real, high-conductivity anomalies. History's greatest lost fortunes are not gone. They are sitting perfectly in place, waiting for the explorer who knows exactly how to read the map. You can perfectly calibrate historical maps in your digital workspace, but a massive physical barrier still stands between you and the dirt, the living canopy. Across New England and the American South, dense vegetation completely blocks standard satellite imagery. If you are looking for centuries-old homesteads or deep earthen fortifications hidden in these woods, looking down from space will only show you treetops. LiDAR, light detection and ranging, bypasses the canopy. An aircraft fires millions of laser pulses. Many hit branches, but some slip through to strike solid soil. Software filters out these first reflections, exposing a bare-earth digital elevation model, revealing the naked ground. By stripping away the biological layer, you remove the guesswork, turning historical research into precise topographic targeting. When you first import that raw LiDAR elevation data into QGIS mapping software, it usually appears flat and featureless to the human eye. This diagram demonstrates the multi-directional hillshade filter. Standard single-angle shading hides subtle geometry. Multi-directional shading calculates multiple angles simultaneously, forcing faint historical depressions into 3D relief. Here, a target vector pinpoints where an old property boundary intersects this newly revealed LiDAR anomaly. You isolate that specific intersection and drop a digital pin, exporting those coordinates out of the software as a GPX track file. You then load those tracks into an offline mobile mapping unit. As you walk the actual terrain, your real-time GPS position tracks directly over the transparent, historical, and LiDAR hybrid layers on your screen. All of this advanced digital processing is designed to do one thing: narrow thousands of acres of wilderness down to a single actionable square yard. At the GPS coordinate, the digital phase ends. You must immediately lay a physical baseline, pulling a 30 by 30 foot string grid tight across the dirt. This string acts as an absolute physical boundary. It governs your movement and prevents wandering off target, guaranteeing total soil coverage over the anomaly. This diagram illustrates a 12-inch metal detector coil. Stepping forward 12 inches leaves deep triangular blind spots in the soil. To seal those gaps, use a 50% overlapping sweep, advancing only 6 inches per step to achieve absolute ground coverage. Extracting deep, heavily masked caches requires extreme physical discipline in the field to match the exactness of your software. Physically isolating an anomaly is only the midpoint of your journey. The final barrier between a successful preservationist and illegal looter is deliberate legal protocol. In the UK, you operate under the Treasure Act 1996. The law applies to any object at least 300 years old, containing at least 10% gold or silver by weight. If you recover an item meeting those criteria, you have a strict legal obligation to report the discovery to the Portable Antiquities Scheme within 14 days. The artifact is then officially evaluated by institutions like the famous British Museum. If a museum acquires it, an independent committee determines its market value, resulting in a 50-50 financial split between the finder and the landowner. In contrast, the United States relies strictly on property-based laws. On state, federal, or national parklands, the Archaeological Resources Protection Act, or ARPA, enforces a total prohibition on unauthorized detecting or digging. Violating ARPA by extracting an artifact over 100 years old from public land is a major felony. It carries severe penalties, including asset seizure and prison time. When searching in the U.S., you operate on private property under the contract rule. Before stepping onto any field, you must secure a signed landowner permission deed that grants you the right to excavate and explicitly defines a 50-50 asset split. Remote sensing technology gives us the power to see the invisible, but human history is actually preserved through strict physical methodology and absolute adherence to legal ethics.